Welcome class to our number 2 lecture for Advanced Aircraft Systems. Today's lecture will be covering the APU and external power sources for the aircraft. Normally these power sources are used when the main jet engines are not running and the aircraft is on the ground. There are exceptions to this rule for the APU, but today we're going to think in terms of the aircraft being parked at the gate or parked out on the hard stand on the ramp somewhere. So let's get started. And here we go. The APU and external power. This module covers the auxiliary power unit and other sources of power that are provided to the aircraft when the main engines are not operating. So we've just said that. We've said it again. Get my screen set up here so we can do things in a more appropriate way. And to our next slide. Come on. Here we go. First thing we're going to talk about briefly is a cold, dark airplane. This term is applied to an aircraft that is unpowered. Generally, it means no electrical power is available to the aircraft and engines are not running. Usually, this condition is how the aircraft is left when it is at a gate overnight or parked elsewhere on the ramp. So what it really means is there's no electrical power on the aircraft and no pneumatic power. It's just sitting there parked somewhere. And when you approach the aircraft early in the morning, if you're an AM flyer like I was in the airlines, I like to fly early in the morning, you could often get to the aircraft. The lights are all turned off, there's no power on it, and you had to get this aircraft powered up with electrical power so that you could even function, so you could read the instruments, set up your FMS, those kinds of things. So a cold, dark airplane is when there is nothing available to power the aircraft with, or it's at least not powered at this point in time. You might have some power available, but it's not been plugged into the aircraft or the APU is not running. So that's what a cold, dark airplane is. You'll get used to that term. You'll hear it time and again as your airline career advances. Sources of power for when an aircraft main engines are not running. Now, when I say sources of power, what we're really talking about here is 115 volts, 400 cycles or 400 hertz. Get used to that number, 115 volts, 400 cycles. This is a common set of power units that aircraft operate on, the big aircraft anyway. This is not your typical 12 volt Cessna 172 system. These are big airplanes, requires a lot of electrical power. So for efficiency purposes, they use 115 volts, 400 cycles. And this takes either a source of ground power or electrical generators producing this type of power. We have two types of power: internal power, which is supplied by the APU. And as you can see right here in the back of this airplane, this is the back of a CRJ 700. They have lifted the cover up and the APU is right back here in the tail of the aircraft. Auxiliary power unit. Another source of power, electrical power, can be provided by fixed ground power. This is often referred to as gate power. Gate power comes from the building that is sitting next to the aircraft, probably hardwired into the building from the electrical company. Anyway, they would take a drop cord out from the building or the jetway, plug it into the side of the aircraft, and that would be called gate power. Another form of power is portable ground power units. These are referred to as GPUs, ground power unit. And this is nothing more than a portable generator on 4 wheels. They can pull it around with the tug. They can pull it from one airplane to the next. And they can use it in cases where they do not have ground power available, or if they've got an aircraft out on a hard stand on the ramp where there's no gate power available, they can plug it GPU into it and get power that way without having to start the main engines. Let's talk about the APU overview for a second. The APU is nothing but a jet engine that does not produce thrust for the aircraft while it's airborne. It can be used airborne in certain cases. For example, if you had an engine failure, you might want to turn the APU on to have a backup source of electrical power in case something happened to the other main engine. Obviously, these are what we call electric jets. You would want to make sure that they always had electrical power available to them when they're in flight. Okay, while on the ground, other sources of power are not available. The primary purpose of the APU is to provide electrical power to the aircraft. Again, 115 volts at 400 cycles. And because it's a jet engine, we can siphon off some pneumatic power to run the air conditioning system, and we can siphon off pneumatic power to help start the engines. So 2 sources of power. We have electrical power and we have pneumatic power. So keep in mind that we generally start the APU up first before we start the main engines. The APU is a smaller jet engine. We need that source of bleed air off of the APU to get the other engines, the main engines, rotating. They do that by a mechanical starter motor, which is pneumatically operated. That starter motor is mechanically attached to the N2 shaft on this particular aircraft engine to make that main engine start rotating before we actually add fuel to the burner can and light it off. So we have to have an airflow going through those jet engines. We have to get those jet engines turning. We use the APU air source to do that to an air starter motor, again, attached to the N2 shaft, and that mechanically makes the jet engines turn, and voila. So I'll pull this up out of the way. A little better view there of our electrical diagram. APU is an electrical source. When there is no other source of electrical power available, the APU can provide power to meet the entire needs of the aircraft electrical system. When properly operating at 100% RPMs, the APU engine directly turns a dedicated generator at the required RPMs, producing 115 volts, 400 cycles. The APU operates at a constant 100% RPMs to maintain a constant electrical output by the generator. Unlike the main jet engines, the APU is not variable in speed. So let's talk about that for a second. The APU runs at constant RPMs. Once it starts, it spools up to 100% of its rated RPMs. I don't really care what the actual RPMs are as long as it's running at 100% of the rated RPMs. The reason this is important is because the generator that is dedicated to the APU is basically geared to the main shaft of the APU. If that main shaft is not spinning at 100%, then the generator is not spinning at 100%. If the generator is not spinning at 100%, then it's not going to turn out 115 volts at 400 cycles. So therefore, we would not be getting the proper type of electrical power onto the electrical system of the aircraft. So that's very important. So we do not have a throttle on the APU. When we start it, it runs at 100% RPMs. So when no other source of electrical power is available, this is when we would start the APU. So in this case, we have this depiction of the left engine generator, and we have a right depiction engine generator, and the APU is shown here in the middle of the schematic, and it is powered. The APU generator is shown here. It is powered by the APU. When the APU is operating and the main engines are not operating, the relay attaching the APU generator to the cross ties that carry the electrical power over to the AC bus number 1 and AC bus number 2, where the electrical power is distributed throughout the electrical system. Okay, so several things have to happen. The relay here has to close, the relay here has to close. The relays coming from the main engine generators are opened, and that's how electrical power is provided for the electrical system by these relays opening and closing in the correct sequence. APU as a pneumatic source. So the APU is a jet engine. It's going to produce bleed air that we can siphon off to run certain things like the starter motors when we're starting the main engines, and it can run the air conditioning system by providing air to the air conditioning kits, or the pneumatic air conditioning kits referred to as packs. So during normal operation, bleed air from the operating APU can be used as a source of air power for the aircraft's pneumatic system. When the pneumatic system is pressurized from the APU, the pressure can be used to provide air to operate the air conditioning system. Also, the pneumatic system is used to supply air pressure to each of the main engine's air starter motors to get each main engine rotating for the purpose of starting while the aircraft is on the ground. Can also do this in the air, but typically we would use the APU to start the engines on the ground. As a pneumatic source during ground operations, APU is a pneumatic source. So when other sources of air are not available, the APU can provide bleed air from the APU engine compressor stage for the air conditioning system. So just like the main engines, the APU is a jet engine. It has a compressor built into it, and that compressor is where we siphon off bleed air so that we can use it in the pneumatic system on the aircraft. Where normal main engine starts, the APU bleed air is used to turn an air starter motor. We've talked about this briefly on each of the main engines, one at a time. The APU does not produce enough bleed air to start both engines at the same time. These main engines take a lot of air pressure to get that starter motor to turn the main engines over and get the rotation started so that we can add fuel to the burner can and then eventually light off that fuel air mixture. And then that would, of course, keep the engines running. So let's take a quick look at this. So here's our APU down here, and we would open this valve, get a pin here, maybe I can provide the information to you. So the APU is right down here, and this is what we call the load control valve. Once the APU is running, we have available pneumatic air. We would open this valve. The air pressure would then come up and come across. This is the isolation valve. This is going to be an important valve to understand later on. But the air comes up, pressurizes this cross duct, and then goes up this way. The start valve would open, would then allow air pressure to go to this starter motor, which is mechanically attached to the N2 shaft. The N2 shaft starts to turn. The N2 compressor starts to turn. At the same time, the N2 turbine starts to turn. This in turn starts sucking air through the engine. That would rotate the fan because of airflow going through the engine. And then one turbine would start to turn. As soon as that all happens, then we can add fuel to the burner can and light it off, and voila, we have the engine running. And then we would disconnect the starter, or the starter disconnects automatically, closes the start valve, and then we would open the isolation valve. On this aircraft, it happens automatically, and then we would start the other engine in the same sequence. So that's how we use pneumatic source to start the engines. All right, moving on to the next slide. Now, how do we start the APU? Well, we start the main engines using pneumatic air sources because they're really big engines and they need a lot of air to get started. The APU is a smaller jet engine. It will actually start using battery power. It does not need a source of air power to start the APU in this case. Excuse me. So we have a few things associated with the APU. The most important thing is the computer that runs the APU. So this is the ECU, the electronic control unit. It handles all the functions required to get the APU started. It runs an actuator here, tells the actuator to open so that a door here, inlet door here to provide air to the APU can open. And it also tells this panel here what to do, or when you start selecting buttons to get the APU started. This panel is located on the overhead panel in the cockpit of the aircraft. It's what we call our APU panel, APU start panel. It's how we control starting the APU and shutting the APU down when necessary. All these components work together. The APU is the brain, or the ECU is the brains. The ECU is the computer that contains and monitors the APU throughout all phases of operation. The ECU will automatically control the APU door opening, and on the ground, the ECU will automatically shut the APU off for these reasons. We have an APU overspeed, because we don't have thrust levers on it or a throttle on it. Something has to control those, control the APU RPMs. That's what the ECU does. If it recognizes an overheat, the APU will shut down. If it recognizes an APU fire, it will shut down. If we have a hot, hung, or no light off when starting the APU will automatically shut down. In the case of low oil pressure, it shuts down, and an underspeed and other APU faults will monitor other APU faults as required to detect that there's an abnormality existing with the APU. We looked at that slide. Let's go on to this one. The APU fuel source. Well, what kind of fuel does the APU run on? It would make sense that it would want to run on the same fuel that the jet engines run on. And since that is the case, it's running on jet fuel, we would like to take that jet fuel from some tank somewhere on the aircraft. Well, we're going to take it from what we call the left collector tank. Well, the left collector tank is just one of the tanks on the aircraft. You'll learn about that in fuel systems. But for the time being, let's just take this as basic fact. On the CRJ, fuel is supplied to the APU from the left collector tank that is fed by the left main fuel tank. There are two collector tanks, the right and left. To supply fuel to the APU, the APU selector valve must be open. This is accomplished by pressing the power fuel switch on the APU overhead panel. On the flight deck, once the fuel is available to the APU, the start stop button can be pushed to start the APU. Now, of course, I said that the ECU controls all of this. So let's go through a little bit of what we're going to end up doing. Here we have the power fuel identifier for this button. That's the power fuel button. When we push that button, we're telling the ECU that we want to get ready to start the APU. The ECU then will do a lot of little things like open the door for the APU and get ready to give us some APU engine indications on our ICAS. It will also open this valve here on the schematic. Right up here is our collector tank. And note that the left engine also gets fuel from the collector tank down this way. But in this case, the APU is also getting fuel from that tank, and it's got a pump on it that pumps fuel down to the APU. And unless this valve is open, the APU can't get fuel, therefore it's not going to start. So when we push the power fuel button, this valve would open on the and then provide fuel to the APU. And this is a status page that shows that the valve is closed. Again, when we push this button, we could go to the status page and we'd see this valve open up and we'd see the green line coming down this way, providing fuel to the APU. So we have this schematic in the aircraft. We can look at it on the status pages to make sure that it's all functioning properly. So power fuel button opens that valve and a few other things occur, but without getting this valve open, the APU is not going to start. Here's what the start sequence is that the ECU is commanding. So the ECU, the electronic control unit, being the brains of the operation. Nope, the pilots are not the brains in this one, but the ECU is taken over for the pilot and is setting up the sequence to start the APU. Now, when I was a flight engineer on the 727, we did not have an ECU. We were the ECU. We had to make sure that everything was going according to plan when we started the APU, and we did not want to have an issue at this point in time. This was kind of like a Jeopardy event when we started the APU. The APU, if it malfunctioned, could literally burn the aircraft down to the ground. So we monitored this like a hawk, or at least I did. I was afraid. So I wanted to make sure that everything was going according to plan and that the sequence was followed to the T. And if there was a fire that erupted as a result of starting the APU, I wanted to make sure I had my little memory item. I'd want to know where the stop button was, and I'd want to arm the fire bottles to make sure they were available. So it was off and agent armed. And then if I had a fire, I could put the fire out using the extinguishing agent in the fire bottles. So today we have the EEC that does that for us. So it's a little less stressful to start the APU on these modern jet aircraft. Various things happen during APU start sequence. It is incumbent on the pilot to be aware and monitoring what is occurring. So just don't take it for granted. This is all going to go according to plan. Stay in the loop, watch what's going on. First thing, of course, we said we were going to push the power fuel button, which is, as I've said earlier, is that button right there. Here's what's going to happen. The EEC is going to get powered. The air inlet door is going to open. We're going to get an APU invite enunciated. And it should be in here somewhere. I guess it didn't show up yet in my picture, but somewhere up in here, you'll get an APU invite appears. That's doing a test on the EEC to make sure the EEC is working properly. Not the EEC, but the ECU. And the door is going to be enunciated as being opened. And the APU SOV valve, that was our shutoff valve going to the APU, providing fuel, is open. And the RPM and engine gauges appear. So here's our RPM gauge. And here's our exhaust gas temperature gauge. So all this stuff is happening. We would double check to make sure it all actually occurred. Once this has happened, then we can go ahead and move to the next process of starting the APU. And that is to push the start-stop switch right here. So once we've got the previous indications showing, then we can press that start-stop switch. Basically, you can push it as soon as you see this happen. This is the last annunciation you get in the sequence of the previous slide. Once that door open appears, you can pop on that switch, the start-stop switch. The APU start is showing on the ICAS and start portion. So here's the APU start switch. Pops up and you go, okay, we're good to start. The fuel control unit FCU fuel solenoid SOV opens and ignition is activated. So now we're getting fuel to the APU and the igniters have started. The RPMs start to increase. We can see that right here. This line right here starts to increase. And as soon as it starts to increase, we'll see the EGT line starting to increase right here. And once the RPMs on this line get up to 100% right about here, we know we've got a good start on the APU. The other indication is the lights are going to come on, the buses are going to get powered, life is good, and we don't have to worry about so much the aircraft burning down and having to exit the aircraft, taking our trip to the chief pilot, and being asked, why did we burn down a perfectly good aircraft? So this is when life is good. We have power on the aircraft. Additional assigned studies on the APU. So what I want you to do at this point in time is go to the auxiliary power point unit in your AeroSim. You're now getting used to doing this from the previous APU information on the engines. Now we're just going to go ahead and go to the APU study on your iPad. We're not done yet. Got a couple more items to cover. And we talked, this will be a discussion on external power. This is not in your iPad. This is not specifically related to the CRJ 700. So this is just a little bit more additional information. So external power is used for the purposes of providing electrical power to the aircraft when the APU is shut down and the engines are not running. Why would we do this? Well, fuel conservation, noise reduction, and for other safety reasons, just to name a few. Let's talk about the ground power unit right here. The GPU, the ground power unit, is often used where there's no other source of power available. This is a portable source of power. It's on four wheels, generally speaking, because of their portability. GPUs are often used at hard stands out on the ramp area, at unpowered gates, and during maintenance operations. In this case, it's a maintenance operation. They don't want to run the APU inside the building, obviously not going to run the main jet engines. So for safety purposes, they've got a GPU parked in here, probably close to the door, and maybe putting out some carbon monoxide. They want to keep the hangar free of that, so it's probably close to the door. And they've got a big long drop cord plugging in to the external power port on the side of the aircraft. And in this case, I suppose that might be a CRJ 700. So think of the GPU as being a portable APU for the purposes of supplying external power to the aircraft. Gate power is provided at the gate. It plugs into, this is a different airplane, it plugs into the side forward left side of the aircraft, or correction, forward right side of the aircraft on this airplane. We use gate power whenever it's available when the aircraft is parked at the gate, just to keep electrical power on the aircraft. So think of this in terms of when and how we use gate power typically. So we've just landed the aircraft, we're exiting the runway, we're taxiing down the taxiway. Before we get to the gate, we would actually start the APU, because in anticipation of shutting the engines down, we get the APU up and running as a backup source of electrical power on the aircraft. So the aircraft stays electrically powered while there are passengers on board. We taxi the aircraft up to the gate on the J line. Then we pull the jetway up to the aircraft engine. At the same time, the ground crew is giving us a signal that they have plugged in the external power. Well, we don't care. We're shutting it down the main engines. The APU now takes over, picks up the electrical power requirements. The ground crew then plugs in the ground power. Once the ground power is plugged in, then we can go ahead and shut the APU off. And throughout this process, we have not lost electrical power to the aircraft. At that point in time, the passengers are going to go ahead and get off the aircraft. Aircraft remains powered for the next group of oncoming passengers, and they can get on the aircraft. The reading lights all work. Voila, we're all happy. And we would then, before we push the aircraft, we would start the APU. Then they can pull the ground power, and they would push us off the gate. At that point in time, we'd use the pneumatic air from the APU to start each of the main engines, and we're back on the road again. That's kind of the sequence of events that happens in the airline business for getting the aircraft powered up, keeping it powered up as you come into the gate and at the gate and pushing off. So that's it for this lecture. Hope you got something out of it. In the meantime, just keep in mind, I love my job. Glad to be here. Hope I can make a difference.